Today, I'm going to talk about PN junction diode equation and math physics. Let's start. First, let's talk about this semiconductor. This semiconductor is doped at different concentration, left side and right side. So left side is n-type semiconductor, but however, right side is p-type semiconductor. So uh, because of that different dopant and acceptor concentration, there are different depletion layer in here. So the depletion layer's length is different the left side and right side. You can see the difference of two, and we call this region, this layer, WN to WP. We call this region depletion region. In depletion region, there are no mobile carrier. There are only fixed charge exist. This is very important concept of this chapter. So because this uh, influence the current flow, so we should know there in the depletion region there are only fixed charge exist. However, the left side and right side there are mobile carrier exist and fixed charge are exist too. So this is the semiconductor which is doped differently. So based on that semiconductor, we can draw a four graph. First, we can draw a charge density graph. This is charge density graph. It looks like step function. In the xn to x0, there are n-type depletion layer. This reason is, then we can draw a graph. Multiply dopant, the number of dopant. So we can draw the graph like this, and x2 and x0 to xp it is p-type semiconductor depletion layer. We can draw a graph based on minus q multiply and the number of acceptor. So we can calculate the current density, charge density, and draw a graph like this. Then let's integral this graph, charge density graph. If we integrate charge density, we can obtain the electric field graph. This is electric field graph. Xn to x0 is looks like this, and x0 to xp looks like this. Based on this equation, we can calculate the electric field, and on the x0 they has electric field will be maxed in here. N-type semiconductors electric field and p-type semiconductor electric field should be same in the x0 because this is the boundary of n-type and p-type. So on the boundary there are electric field will be max. So also we can know the depletion layer has an electric field because there are no electric field on the left side and right side. However, xn to xp, the depletion region has an electric field. This is an important concept, I think, in this chapter. Then integrate one more that electric field graph. This is potential energy graph. We can draw a graph based on this equation. Yes, then after we integral the electric field, we should multiply minus. So the potential energy should be have negative value like this. This is x0. Then after based on that concepts, we can draw out this energy band diagram. This energy band diagram uh, looks like this because they are doped differently, left side and right side. So energy band diagram will be changed like this. Because of the difference because of the difference of doping concentration, the left side and right side will be have a different Fermi level. So it means different Fermi level in here, and uh, conduction band energy on the right side minus left side conduction band energy band. This the gap between the two of this, it means built-in potential energy. So we should know this built-in potential energy exists in this semiconductor, which is doped differently, left side and right side. Then let's talk about diode equation. This is current graph of that semiconductor before we talk about until now. Um, there, the drift current in this semiconductor, uh, current will current is the sum of drift current and diffusion current. So I draw a drift current and diffusion current on this graph. So green line is the drift current and the yellow line is diffusion current. However, in this semiconductor, this is a little bit special. So drift current in the left side and right side, not without depletion reason, there are no electric field. Before we draw an electric field graph, the left side and right side, there are no electric field in here. So in this, based on that concept, we can know there are no electric field in here in that left side and right side. So in this semiconductor, we should only focus on the diffusion current because diffusion current uh, only influence the semiconductor. So yes, we should know about the diffusion current in here. Then let's talk about forward bias. If we apply the forward bias, the conduction band built-in potential energy will be smaller. So the conduction band will be energy band diagram will be drawn like this. The red line is the after we apply the forward bias, and uh, when we apply the forward bias, the depletion layer width will be longer and the depletion region's height will be smaller. So the height will be smaller means the built-in potential energy is smaller, and it means also the barrier is smaller than before. So electron on the left side will can move easily to the right side. So if when the electron move easily, it means also the current flow will be higher than before. So after we apply the forward bias, the current will be flow more than before. Then let's talk about reverse bias. When we apply the reverse bias, the built-in potential will be bigger. So the red line graph is revert after we apply the reverse bias. The built-in potential will be bigger, so the barrier will be higher. So electron and yes, carrier cannot be moved easily to the other side. So it means the depletion layer width will be smaller. However, the depletion layer with version's height is bigger than before, longer than before. So electron can carrier cannot move easily. So current cannot flow well. So it is important concept the difference of forward bias and reverse bias. Lastly, let's talk about avalanche. This is the one carrier can make a lot of electron hole generation. This is at reverse bias situation. So the electron carrier collision something and then make a lot of electron hole generation. So today we talk about p-n junction diode equation and math physics. Today, I think this concept is very important to make a good semiconductor because this current, when we adjust the apply voltage, we can adjust the current flow. So if we applied more forward bias, the current will be flow more than before, and when we apply the reverse bias, the current will not be flow. So this is very important concept to make a useful semiconductor, I think. So thank you for watching my video. Bye.